Next up, we have Nazli Dereli, a data scientist at Ticketmaster, presenting adversarial attacks, a real threat to our machine learning systems. Nazli, a reminder to start your timer. I will give you access to share.
Hello, thank you.
You're welcome.
Let me start. Okay, can you see my screen?
Yes, we can see your screen.
All right. Okay, so hello again. Thank you for having me. I'm Nazli. I worked as a data scientist in abuse prevention team at Ticketmaster for the last 5 years. My work heavily focused on adaptive abusive behaviors and designing of ML systems to fight back against bots, brokers, ticket scalpers, and any kind of automated systems. And today I'm going to talk about adversarial attacks, what they are, what different types of attacks they are, and I will talk about some specific real world examples, and then I will discuss some existing methods for defense against these attacks. Okay, so first, what is an adversarial attack? So machine learning systems are often designed for static and benign environments with some assumptions. However, when we deploy these systems to production in real world, the reality is very different from the assumptions because people can actually have malicious intent in real world. Adversarial attacks are basically inputs to our ML models that are intentionally and maliciously manipulated to trick the model. And they can expose so many fundamental blind spots or vulnerabilities we need to cover in our ML systems. And I think this is why it is very important as data scientists to learn about these attacks and the vulnerabilities that they might exploit. So this table summarizes some aspects of different types of adversarial attacks. This first column here is the timing of the attacks. So it refers to where in the machine learning pipeline the attack happens. So in a supervised learning model, it can happen either during the test time or during the training time. Okay, so this figure shows it more clearly. So here we have a basic machine learning pipeline. We have our training data on the far left, which feeds into a machine learning algorithm. And then the model is trained. And using this model with test data coming in, the model makes a prediction and outputs a result. So in terms of timing of adversarial attacks, the attack can either happen here during the test time, which means the attacker is only able to modify the immediate input data. So this may or may not be a powerful attack based on your model, but it is certainly much easier to perform because the attacker only needs a way to inject modify input into the model. And the other option is to attack during the training time here. So this means that the attacker is able to influence the training data set of the model, either by reducing or eliminating its efficacy. So this is a very powerful attack, but it is very hard to do because it requires a very good understanding of the insides of the model. So going back to this table, the rest of the columns are for the adversarial goal, which can be either integrity, availability, or privacy. So integrity attacks are for making an ML model make mistakes, but without being detected. And availability attacks are for taking an ML system down entirely, making the model useless. So these are very similar to DOS attacks. And privacy attacks are for extracting sensitive information from an ML system. So as you can see from this table, in terms of timing and the adversarial goals, there are three types of adversarial attacks: evasion attacks and privacy attacks that happen during the test time, and poisoning attacks that happen during the training time. So in this talk, I will cover evasion attacks and poisoning attacks so that I can cover both test time and training time. Okay, so the first type of attack is the evasion attacks. So this is the most prevalent and most popular type of attack. And as I mentioned before, it happens during the test time. So the attacker modifies or perturbs the input data to throw off the model and to evade detection. So in here, this is a very simple example of it. So this is an image classifier, and it classifies image as a panda or a gibbon. So without any attack with this first image, this is a clean image of a panda. The classifier accurately classifies this as a panda with 57.7% confidence rate. But with an evasion attack, usually there is a certain level of noise like this one that cannot be detected with human eye. So this noise is added to the clean image, and the modified image is given to the model. And now with this modified image, the model, the classifier classifies it wrongly as a gibbon, and it has a very high confidence rate too. It has 99.3%, which is very scary. Okay, so this is another cool example of evasion attacks. So these glasses are adversarial glasses. They are to full facial recognition softwares. So they either dodge the face detection altogether, or they impersonate someone else, like in these images. And also use of stickers is another example. So in this example, they put stickers on top of stop signs, and the stickers are perturbed to mimic graffiti, because apparently there are usually a lot of graffiti on traffic signs. So they use this to fool the classifier to classify this stop sign as a speed limit sign or any other kind of traffic sign. And this sticker is called an adversarial patch. This is to fool models to output a targeted class. So they place this patch on the input image. And the cool thing about it is that they don't need to know what image they're attacking when constructing the attack. It works in either way. So in here, just with the banana, the classifier classifies this accurately as a banana with a very high confidence rate. But when you put the patch on the image, the classifier classifies it as a toaster. And again, it has a high confidence level. Okay, so now I'm going to talk a little bit about some known methods of defense against evasion attacks. So one of the methods is called adversarial training, which is a brute force solution where we explicitly train the model with adversarial examples. And the downside of it is that it only defends the model against the same attacks that we train it with. And also when we train the model very often, now there is too much fake data in the training set, and this messes up with the decision boundary of the model, and basically it becomes useless. So like in these images, in the first image, so there are these two red spots, which are the adversarial examples that we want to train our model with. And when we train the model with them, see the decision boundary changes significantly from this one to this one. And with this new decision boundary now here in these two spots, they are now lie on this side of the boundary, and these other two spots lie on the other side, which means these points, these data points are classified wrongly. So our classifier became useless. Another defense method is called gradient masking, or specifically defensive distillation. And this is a method that tries to deny the attacker access to powerful gradients. So this basically makes it difficult to figure out where the holes in the model's defense are, but it doesn't make the model more robust. So the attacker can still train their own model, which has a gradient, and they can make adversarial examples against that model and then transfer those examples to the model that they want to attack. So this is not a very effective way of defense, but it makes it difficult for attacker to attack. So this is our second type of adversarial attacks called poisoning attack, and this happens during the training time. So this poisons the training data set by injecting bad data into it, and this eventually compromises the learning process. So for example, here we have a classifier with this decision boundary, and if we change even one training example here, like this one, like in this case, the label of it even doesn't change. And even that changes the decision boundary significantly, and it affects the classifier immensely. So these are very dangerous attacks. Yeah, so this is a very interesting example of this. So this is Microsoft's chatbot for Twitter. It is called Tay, and it was implemented in 2016, I believe. So this bot was supposed to learn how to make conversation through chatting with people. And within less than 24 hours, it starts to tweet like very misogynistic and racist tweets. Because that's what it learned from all the users in Twitter. And again, some known methods for defense against poisoning attacks. So anomaly detection can be used for these attacks. It is to detect training examples that are very different from the rest of the training data set. This might work in some cases, but not all. For example, if the injected data points are similar to the true data distribution, then this doesn't work. Or if data points are injected before filtering rules, then they are not anomalies anymore. So again, this doesn't work. Another method of defense is could be to analyze the impact of newly added training examples on the model's accuracy. So the idea here is that, like, if there are poisonous training examples, then it should affect the model's accuracy on the test set. So it would be a good idea to do a sandboxed run on the new training examples before adding it to the production. Yeah, so that's the end of my talk. Thank you for listening, and I can do the Q&A now.
Yeah, thank you so much for the great talk, Nazli. We'll now transition to the Q&A. Remember, attendees, to upvote the questions that you would like to see answered. I'll turn it back over to you. Do we have any questions?
I don't see any.
Wow. answered them all. Attendees, do we have any questions? Just give it a minute. So Nazli, I see some nice chat comments. Folks enjoying the chat, but I don't see any questions. If folks decide they have questions later, do you have any follow-up or contact information if you're open to that?
Oh, I didn't put any contact information. I will be online in what was it called? Brella. So I can chat or talk through that there.
Fantastic. Okay, we have a question that popped up.
Oh, there is?
How much does this cost companies with it going awry? Can you see that one?
Yeah, I can. I don't actually know the real cost, but it is a trade-off. I mean, like, of course, like heavily investing in this kind of like protections is expensive, but there might be like some like cheap like introductory defenses that can be used to start with. And I think it is good to start with something, because like anything is better than nothing. So yeah. So again, like adversarial model it's not very different from the real models, but if we just have like these different defense methods incorporated in them. And again, like there are some like easy to do, like low hanging fruits kind of like defense mechanism that I mentioned, which are not that costly and they are good to start with. And then based on the feedback, like based on like what kind of attacks are happening, what kind of like data we are seeing, we can like move forward from there.
Two more popped up.
Data augmentation. Yeah, it can be used. Again, like I didn't try that in production myself, but I think like if you based on, you know, the cost of it, based on what you have, you can do it. It could help in your training. Again, these are like very like domain specific, model specific mechanisms. So based on like what the model is trying to achieve and based on what kind of attacks you are getting, there are like many methods that can be tried and put into use.
And I think we have time for this last one.
How can companies ramp up their security models? This is very similar too. So again, like I professionally like recommend using first the easiest and very like low hanging fruit, like cost effective mechanisms that I mentioned. So for example, like anomaly detection or like doing more testing with your training data set. These are like not very hard things to do. So yeah, I think starting with those would be a good way to start securing our models.
Fantastic. We're going to wrap up and move to the next speaker. So thank you so much for your talk. This was fantastic. Lots of great feedback in the chat. So